Okay, so there we go. Estimating with finite sums. Suppose a car is traveling at 65 miles per hour for 2 hours. What is the accumulation of miles for the sum of this instantaneous rate over a 2-hour period? Okay, so I have a little graph here. We're going to talk about this graphically. So we have a car that's traveling 65 miles per hour, a constant 65 miles per hour. They're on 80, traveling past the salt flats in Utah. And they set the cruise control. When you set the cruise control, when you're going past the salt flats in Utah, your car does not vary up and down. It's not like the hills around here where you go uphill so it slows down, you go downhill, it speeds up. No, when you're going through the salt flats of Utah, it is flat. And your cruise control does not change for anything unless you put your foot on the brake or the gas. I've done it enough, trust me. And there's nothing else to see. So you set it about 85 because the speed limit's 80. You set it about 85. You can probably get up to 90 as long as you don't look like you're carrying drugs in your car. They won't pull you over. No, I've actually heard that from State Patrol in Utah. You don't look like you're carrying drugs. They're not going to pull you over for speeding in Utah. Okay, and you just go because there's nothing to do. Okay, so traveling right along at 65 miles per hour. That is a constant speed, right? Okay, it's a constant speed. That would be a flat, straight line. It's constant. How do you graph a constant? Y equals that constant, right? For a 2-hour period. Let's make this interesting. Between 1 o'clock and 3 o'clock, just to make it interesting, but any 2-hour period will work. Okay. What is this measurement here? This distance here, or I should say the height. What is this? What are the units here? What are the units? Miles per hour. Miles per hour. What are the units across here? Hours. What happens when I multiply miles per hour times hour? You get miles. Miles per hour times hour equals miles. So if I were to multiply the units on this side times the units on that side, I get what? I get the units of miles, the distance traveled, right? So if I want to look at this geometrically, what am I doing? I'm finding the area of this space here. 65 miles per hour. 2 hours. 65 miles per hour times 2 hours equals 130 miles. So I've traveled 130 miles. You're going at a constant rate. It's easy. The key idea to this is the area. What did I do? I took a rate times the base of that rate times the time period that it passed, and multiply those two together, you get the amount that happened. You take the instantaneous rate, and it is an instantaneous rate. How fast am I going right here? How fast am I going right here? How fast am I going right here? So this is a collection of instantaneous rates, correct? But it's a constant. All of them are the same. But if I take that rate times the time, okay, and as long as the units match, if they don't match, you must make the units match. Okay, I get the distance traveled. Algebraically, I multiply it. Geometrically, I'm talking about the area. So if I have an equation that describes a rate, and I have a graph like this where my rate is the y-axis, and my time period that the rate is measured in is my x-axis. I multiply those together. I find the area underneath the curve between the beginning and ending points. I have found the distance traveled. When we were doing derivatives, what were we often doing? We were taking distance and finding rate. right? When you take the derivative of the distance traveled or derivative of the position, what did you find? You found the rate. What did we just do? We went the other direction. We took the rate and found the distance traveled. Okay. This is the beginning concept. There's a lot of conceptual ideas going on here. Big one we're dealing with, though, is we're looking for the area under the curve between point A and point B. Okay. Now, it doesn't say from time equals 1 to time equals 3, it's 2-hour period. I picked a 2-hour period. Any 2-hour period, because it's a constant rate, will work the same. Okay, this one's a little different. Same basic concept, though. I have a graph that describes my rate, an equation to go with that graph. Okay, the velocity of this object moving along the x-axis. By the way, this is a very common thing. A particle moving along an x-axis, that is actually called rectilinear motion. Particle moves along the x-axis according to an equation that describes its velocity. That's called rectilinear motion. We're going to do a lot of work with those over the next couple of months. We're going to find out and describe all kinds of crap that's going on with a little dot moving back and forth. Okay, this is an easy one. We're going to get much more complicated as time goes on. But it's called rectilinear motion. Get used to particles moving along the x-axis. Okay. It has a velocity v of t equals 3t plus 2 for all t greater than or equal to 0. We're dealing with time. We do not have negative time. You may have negative position. You may have negative acceleration. You may have negative velocity, but you will not have negative time. Okay, time will not move backwards. Particles may move backwards, but time does not. Time marches on. Okay. Where's the particle at t equals 2 seconds? So it starts at 0. Where is it? So it starts, and this is not a graph of where it is. This is strictly a graph of how it's moved. This is an equation describing its velocity, its motion, not actually its position. So what we're saying is, hey, we've got this situation. We got a little dot that's sitting right here, and it moves. Now, its motion is always going to be in this particular case, it's a positive motion, right? So, because it moves 3t plus 2 is positive as long as t is greater than 0, or actually greater than negative 3/2, right? No, negative 2/3, but it doesn't matter. We don't have negative sign. So velocity is always positive. So this little dot is just going to be rolling along. We want to know, where does it stop? We want to know, where does it stop? Now, we know where it starts, right? It starts at 0 because we're told it starts at 0. We could answer this question if we knew other places where it started as well. The process would be similar. Starts at 0, where does it stop? Okay. Can't really find where it stops directly with the information, but what we can find is how far it traveled. And if we know where something starts, and we know how far it moved from where it started, we know where it is, right? And we can figure out how far it went. Because once again, this is a function describing motion. In this case, it doesn't give units. We don't really care about the units. We do have the time, but it's whatever units per second times seconds gives us how many units it's moved. Same idea. Now I have to roll this up a little bit to give us room to do our work. But we're doing the same thing. When do we start? We start at time 0. When do we end? When does it say we end? T equals 2 seconds. We end at 2 seconds. We take the distance traveled times the rate. We can find how, or we take the rate times the amount of time it was traveling at that rate, we can find it. Now, the previous one was easy because it was a nice flat constant line, right? And so I took this little distance here plus this little distance here and this little distance here. because it's traveling at a different rate all the way along. But if I take this little distance here and add it up to that one and add it up to that one, what do I eventually get? I get the whole thing. What kind of shape is that? No, it's not a triangle. It's a trapezoid. Turn your head sideways. It's a trapezoid. Height, base 1/2 height times base. Oh, I'm going to tell you right now. The area of a trapezoid. 1/2 times the height times base 1 plus base 2. You will need to know this and have this memorized. You have to dig back to your geometry and remember this. If you look at your assignment sheet, these second two last sections, the last section on here is review and test. The one before that is the trapezoid rule. Yeah. Area of trapezoids is a big deal. Areas of rectangles and areas of trapezoids are a big deal with what we're doing in here. Okay? So, yeah, this is a good one because of that. What's our height? Our height is this distance here because, remember, the bases are the parallel sides. So our height is this distance here, the one perpendicular to the two parallel sides. So our height in this case is 2. And base 1, I'm going to call it this one. If I put in 0 into that equation, I get 2. Plus, and if I put 2 into the equation, I get 8. And now you can also get it from the graph. That's okay to get it from the graph. But when you have the equation and don't have a graph, what would you do? You plug the value into the equation. You get 8. So 2 plus 8 is 10, times 2 times 1/2 gives us 10. It traveled 10 units. So where is it now? It's at 10. Area under the curve. It's not a curve. It's a straight line. But we all call all graphs curves, even if they're straight. Okay. You with me so far? It's not bad yet, is it?
No.
Don't worry.
No.
I was worried. What if V of t is not a constant? What if V of t is something that's not a nice straight line? Oh, crap. Well, we're going to find lots of different ways to figure this one out. So suppose f of x, our function, is 16 minus x squared, and we're going from 0 to 4. So we want to find out what's the area underneath this curve shown here. Okay. Now, we will get to a place where we can do this exact, but we don't have the tools yet to do that. So what we have to do is we have to do an approximation. Okay. We're going to do RAM. We're going to do LRAM. We're going to do RRAM. We're going to do MRAM. RAM stands for Rectangular Approximation Method. Okay. My suggestion to you, sketch this curve. It does not need to be exact. Don't worry about it being exact, but sketch this curve. We're going to do this 3 times. We're going to start with LRAM. We're going to do MRAM, and we're going to do RRAM. You're going to be able to compare them. Now, they're an approximation. The important word here is approximation. This is not exact. The only time rectangular approximation method is actually exact is if you're dealing with an actual rectangle. Then why bother doing an approximation? Just figure out the area of the freaking rectangle. You can do that. Rectangles are easy. Space times height. Okay. We're going to do LRAM. Okay. And it gives us some important information. N equals the number of subintervals. In this case, how many subintervals do we have?
4.
We got 4. N equals 4. This is muy importante. The number of subintervals tells us how many rectangles we're going to divide this up into.
So are subintervals always just the ending of the.
No, it's not. Subintervals is just how many subintervals you're divided up into. You might be divided into 3 or 4 or 5. The end point is not, no. It just makes it easy to make the end point the number of them, because then you go, oh, 0, 1, 2, 3, you just break it up into 4, right? But what that tells us is how many rectangles are we dividing this into? Because we're doing a rectangular approximation. How many rectangles? We got 4 of them. And they're all equal width. Doesn't always happen. That's one of the situations, we will talk about that at another time, them not being equal width. But if I have an equation, if I have a graph, I'm doing equal width. Okay. If you have a table of data, you use the width that the data tells you to use. If the data is equal width, you're great. If the data is not equal width apart, then you got to use the data. Okay, so you have to pay attention to that. So LRAM. Okay, I'm going to have to extend the page to be able to get down to the bottom here. So we have 4 subintervals. So 1, 2, 3. There's our 4th one. So we have 1, 2, 3, 4 subintervals. So those are the widths. Now it's nice. Situation, the width is equal. What is the width on each one of these?
1.
It's 1. Okay. We have to find our heights, though. And this is where L and M and R are different. LRAM. Everybody hold up their left hand. Said your left hand. Yeah, I think all right. So when you use LRAM, you're using the left one, which means you use the left-hand side of your subinterval to determine your height. I have 2 sides to each subinterval. I have a left and a right. When I'm using LRAM, I use the left. So my left-hand side of my first subinterval is at 0. X equals 0 is the left-hand side. So my first rectangle, the height comes from there, from the left-hand side of my rectangle. On the second one, same thing. I still have a rectangle. Its width is here. My left-hand side of my rectangle, the left-hand side of my interval determines the height of my rectangle. So for LRAM, I have a rectangle. Each rectangle is a width of 1 on this particular problem. The width may be different depending upon the function and the equation, all that good stuff. But LRAM, I go up both sides. Where the left hand hits the curve, that's where I stop. That's my height. If you have a function that is decreasing, LRAM will give you an over approximation. Notice each one of those rectangles is above the curve. So when I add up the areas of those rectangles, I'm going to get an over approximation. I'm going to get more area that's actually than is actually under the curve. If I have a decreasing function, then LRAM is going to give me an over approximation. So let's do our LRAM. Let's find it. Our area underneath the curve equals width times height, width times height, width times height. Width is 1 times my height. What's the height of the first one? 16. Plus the second rectangle. Width of 1 times the height of my second rectangle, which is 15. And now you can get it graphically, but if your graph isn't a good graph, if it's a harder one to do and we get to MRAM, you're going to see how important this is. Use the function 16 minus x squared. 16 minus x squared. And plug in your x value for the left or right into that, and you get your height, right? Your equation gives you that height. So I put in 0, I get 16. I put in 1, I get 15. Next one, the width is still 1. My x coordinate would be 2. Put 2 in there. 2 squared is 4. 16 minus 4 is 12. And if I go to my graph, I get 12. And then I do the same thing on the last one. My left-hand side of my interval has an x-coordinate of 3. 3 squared is 9. 16 minus 9 is 7. Plus 1 times 7. You add them all together, and actually I should change that to LRAM. Okay. And my left rectangular approximation method gives me 16 plus 15 is 31, plus 12 is 43, plus 7 is 50. You're good so far. Questions so far? Yes. Oh, yes. Yes, we will do them all. So, do you understand left hand? And that's the key between difference between left and right. Left hand, you look at it, you go up the left-hand side, that determines your height. Right hand, you're going to go up the right-hand side. What about MRAM? You're going to go right up the middle, because it's middle. Okay? Does that make sense? Now, we're using rectangles. Why are we using rectangles? Because they're easy. Because they're easy. That's why. We will do other methods later that are not quite so easy, but we use rectangles because rectangles are easy. Like times width. You just got to figure out what those two numbers are. That's an easy thing to do. They will generally have different answers. Yes. Okay. Same thing, only RAM. Okay. Yes, draw the graph. Yes, you want to draw the graph again. It's just, I mean, you could do it on top of one you have. I strongly don't suggest you do that. I strongly suggest you do another one. I used to do them on top, one on top of the other. Oh man, it gets so confusing so fast. If you have a separate one, do a separate one. Okay, same graph, same equation. Like I said, just sketch it. It doesn't need to be exact. You want to get your points of intersection. Other than that, it doesn't really matter. N is still 4. 1, 2, 3, 4. So the widths are all still the same, which is nice. Makes it easy. But our heights are different. Why? Because on this one we're doing RAM. Right. Rectangular. So everybody raise your right hand. Repeat after me. Same idea. You go up both sides. You stop when the right-hand side hits. So in this one, that's my first rectangle. It's a right-hand side, so it goes up until I go up both sides until the right hand hits, and that's where I stop. That's the top of my rectangle. I do the same thing on the next one. I go up and go over. Do the same thing on the next one. And then I do the same thing. Ooh, what's the height of my last one? 0, because I go up. Ooh, it hits right there. So I actually have a rectangle of 0 height, which means I have a rectangle of 0 area. That's okay. Sometimes there is no area under the curve. Okay? That's all right. So our RAM would be the width times the height. 1 times 15 plus width times height of the second one. 1 times 12 plus the width times the height of the third one. 1 times 7 plus the width times the height of the last one. 1 times 0 because it's 0 height. That's okay. Add them all together. 12 plus 15 is 27. 27 plus 7 is 34. If my function is a decreasing function, RAM will always give me an under approximation. If it's an increasing function, it's exactly the opposite. So if you have a function that's increasing, RAM will give you an over approximation, LRAM will give you an under approximation. Okay, this is a decreasing function. This is another approximation. Considerable difference between the two. Okay, considerable difference between the two. At this point, what could you do to find a better approximation? You could do the middle, but what else could you do?
Take the average.
Take the average. That'd be okay. One's over, one's under. The average may or may not, depending on how concave things are, give you an exact value or more exact value than this, but it will be much more exact, may not give you the exact value. So that one was what, 50? 50 plus 34 is 84. Half of that would be 42, right?
Is that right?
That'd be a little more accurate. I could tell you, let's see,
Is that average?
hang on. 16 times 4 is 64. 64 minus 48 is 48? No, one third of 48, 16. 64 minus 16. What's 64 minus 16? 42. Yeah, it's 42 exactly. Because I know how to do it exactly in my head. Because I'm a lot smarter than you are when it comes to this stuff right now. Okay. Okay, are we good with RAMs? You understand RAM? Okay. Now comes the fun one. The one that's just a bit more difficult. The one you're probably going to want a calculator to help you out with. It does not need to be a graphing calculator, but you're going to want to use a calculator to help you out with some of these numbers. Okay. So it's the same idea, only instead of the left-hand side or the right-hand side, you want to go up the middle. So I still divide it in the same number of subintervals. 1, 2, 3, 4. These are my 4 subintervals. Where's the middle of this one? It's at 1/2. The middle of this one would be 3/2. I always like using proper fractions. 5/2 and 7/2. Those are the middle. To find my first rectangle, I go up the middle until the middle hits, and that's the height of my rectangle. Here's my first rectangle, and I know it's not right on, but you guys get the idea. So there's my first rectangle there. The middle is where my height comes from. Not the left, not the right, the middle. I go up the middle until I go up the middle of that interval until I hit. So my first subinterval is still the same length. 1 times, but my height's a little harder to figure out. This is where your calculator comes in handy. Because what's the equation we're working with? 16 minus x squared. Take 3/2 and square it and subtract that from 16. 15.75. Thank you very much. Okay. So before we continue on, you understand where we're getting our values from. We're doing MRAM, which means we're going down the middle. Our left hand is 0, our right hand is 1. What's in the middle? Our middle is 1/2. We go up the middle, 1/2. And that's where our height is determined. It's hard to read the graph. So you use the equation 16 minus x squared, because I just rewrote 16 minus x squared. Take 1/2, square it, you get 0.5. That should be 15.5. No, 15.75, yeah. 1/2 squared is 0.25. That's our height. You do the same thing on the next one. You go up the middle until you hit. And that determines the height of my next rectangle. Okay, that's where my height comes from. Go up the middle until you hit. That determines the height of my next one. Go up the middle until you hit. That determines the height of my next one. Okay, MRAM, you're doing it in the middle. Please finish the problem. You know the midpoints? And decimals are okay for this. Okay. reduce if you use fractions. Okay. What's the height of the second one? 13 point what? 13.75 plus 1 times, what do we get? 9.75 plus 1 times 3.75 gives us a total of 43. So that's not quite exact either, but it's a lot closer, isn't it? What did I say the exact one was? 42? I think that's what I was. And we will do this exact at some point. You will learn a way of doing this exact. Okay? But even that's not exact. It's an approximation. That's okay. Sometimes you cannot be approximate. I mean, sometimes you can't be exact. You have to be approximate. You do the best you can with what you got. And sometimes an approximation is okay. Depends upon the question. Okay? It does. It depends upon the question. Questions so far? Okay. Questions? The idea of dividing an area into rectangles and adding those rectangles together to get an approximation is huge. We will be coming back to this again and again and again. We will come back to this in an extremely important way later on in this chapter. But the idea of taking something and dividing it into smaller pieces and finding the areas of those smaller pieces and using that for your answer would be good. If we had n was 8 instead of 4, would our approximations be more accurate? Yeah. Smaller rectangles, smaller width, little closer, they're going to be more accurate. So that is a big deal. How many subdivisions you divide it up into is a big deal. 4 is a good number because 4 is going to give you reasonable in most situations. You're going to be told how many subintervals on anything you do. Okay, you will be told how many subintervals you have. But it's one of those things, if you do more, now eventually it gets out of hand. At some point you say, whoa, time out. 100 subintervals is too much freaking arithmetic. It's not that much more accurate than, let's say, 10. So I'm sticking with 10 because 10's easy compared to 100. It's literally 1/10 of the amount of work. And it's going to be close enough for government work. At some point, the number of subintervals you break it up into it becomes unwieldy and not worth it. You're not going to be that much more accurate. Most of the ones, 4, 5, 6, is what you're going to do, it's what you're going to be, and you're going to be close enough for anything that we need to do in here. Okay, now, this is great. We got curves, we got equations. This is not the way you will most often see it being done on the AP exam. They will do it with the table of values. Okay, you will have a table of values to work with rather than an equation when you're asked to find rectangular area. Okay? Because if you have the equation, there's better ways to do it. If you have the actual equation and the actual curve, there are better ways to do it. So when you don't have that stuff, you have to do RM and LRM and other things along those lines. And that's what we're talking about here. Okay? So please take a moment to copy this table. Okay, so graphically, you know, what we have going on here is if we wanted to look at this graphically, and this is just a rough estimate, it kind of looks something along those lines. I don't know exactly. I don't care. I really don't care. I'm not trying to find an equation to match this. I don't want to. It's more work than I want to do. Okay? We can. Don't want to, not gonna. But what are we talking about here? Same thing. Area underneath. And how do we find the area underneath? The tools that you have now is we divide it into rectangles. And so we have a bunch of little rectangles. We have all our heights, and some are above, and some will be below, but we're going to divide this area into the curve underneath our rectangles. And this table of data gives us everything we need. What is the width of the first rectangle? 0.01. What's the width of the next one? 0.01. What's the next one? 0.01. You're welcome. They're all the same width. Trust me, because if I am multiplying the same number times a bunch of numbers, what can I do? I can factor it out and just add up the rest of them, right? If I have 2 times 4 plus 2 times 8 plus 2 times 9, what do? I take 4 plus 8 plus 9 and multiply that times 2, right? So if I have 0.01 times the height of a bunch of different heights, what do? I can pull out the 0.01, add up my heights, and then do 0.01 times that height, right? Simple distributing rule. Because remember, distribution goes both ways. When you're pulling out a common factor, you're using distribution. Just doing it in reverse. Okay? So distribution property says we can factor out a common factor. Okay. Same idea here. And here's what's really cool. If you wrote this down like I did as a table, if you have a table on there, turn your paper sideways so that the time is at the bottom and the velocity is on the top. If you don't, then turn your head like this. Because this is my width, these are my heights. So my first rectangle, it goes out until it touches one of those two values. And depending upon which one I'm looking at determines which value I'm going to use for my height of my first rectangle. My first rectangle, okay, and I'm just kind of looking at the first one here. My first rectangle goes from 0 to 0.01, and I go up until I hit that value. And my curve starts here and goes up like this. And I go up until either my left-hand side hits or my right-hand side hits. And you know this is why teachers don't know their left from the right. Because I go to the left, I go to the right, which I'm using what? My right hand. I've actually gotten better as time has gone on. But you go up until you hit the left-hand side for LRAM and the right-hand side for MRAM, or RRAM. I'm not asking to find MRAM. Why am I not asking for MRAM? We can't find it. We don't know. It's a curve. It's not a straight line between each point. We're not connecting dots and finding a straight line, so I can't go in a straight line and estimate. I have no middle value, so I can't use MRAM. I can only use left or right because I'm given data, not an equation. My data dictates. Does that make sense? So all I can do is LRAM and MRAM. So when I'm doing LRAM, my first rectangle, what's the height of my first rectangle when I'm using LRAM? 0. My first rectangle has a height of 0 because if I go up here, if I go up these two here till I get to this point, my left-hand side determines this is my width, and I know that changed it. Well, ignore it. Okay, it's supposed to be 0. I touched the screen. Okay, so my first left-hand one has a height of 0. My next rectangle, I move along here. What's its height for LRAM? 40. I use the left-hand side. I have two numbers. I use the left-hand side for each one of these rectangles. So my first height is, for LRAM, is 40. Or sorry, 0. For the second one, my height is 40. For my third one, it's 60, and so on and so on and so on. What is the height of my last rectangle using LRAM? 137. Because when I go up this last one, my left-hand side is a height of 137. I'm not using endpoints. I'm not using both of those. I can't use both of them as heights. So when I use LRAM, I'm using the left-hand side. The left-hand side is 0 plus 40 plus 62 plus 82 plus 96 plus, right? Add all those together times 0.01. So for LRAM, equals 0.001 times 0 plus 40 plus 62 plus ... plus 132 plus 137 L RAM gives us what? I get what? What? 0.898? 0.898. Do RAM. What's the height of your first rectangle with RAM? 40. What's the height of the last rectangle? 142. So basically take what you did before, what you got adding them together before, and add 142 to it, then multiply times 0.01. Right? Don't add them all together again. You already got it. You should, if you use a graphing calculator, you should have that number on your stack. And what do you get for that? 1.04. Is that what you get? Okay. Questions so far? Yes, ma'am. Okay, same idea. What's our width? We're doing right rectangular. So once again, turn your paper sideways or tilt your head like this. And I'm joking, but I'm also kind of serious. I've actually had students working on something. I take their book and I turn the book sideways. So look at it like this. These are my widths. These are the X values. These are my corresponding Y values. When I do RAM, I pick this interval. I go up. What number am I going to use for the width? I'm going to use the one I hit with my right-hand side first. And the first one I hit was 40. Second one I hit was 62, and so on, to use the last one down here. Okay? Does that make sense? And literally, I've done that with kids when they're looking at it. Turn the book sideways. And it helps you visualize a little bit better.
So you don't actually use like the value straight across the page.
Yeah.
It's just whatever.
Yeah. Now, if they're individual, if the widths are not the same, if you're given a table of values and the widths are not the same, you're going to have to figure out each individual rectangle and add them together. That happens. That's usually what AP does to you. They're usually not so nice, but they also don't give you this many data points. It might be 6, 7 tops. They're not going to give you a lot, and they're going to make it a little easier for you. A little harder to figure out maybe what the widths and heights are, but not a lot of numbers to deal with. They won't have as many numbers as this. For which one? Did you multiply? Is it off by decimals? Did you multiply by 0.001? Okay. I add them together and then multiply times 0.01 at the end. Multiply them in and then add them. You should still get the same thing. Check your arithmetic. You did it right. You probably screwed up and missed the number somewhere along the way. Okay. Questions? So I do believe. Yep, that's it.